do, do, do. terms of real technical content, today we have a guest lecture from Bunnie, Andrew Klein. He was an MIT student a while ago. He's done a lot of cool stuff in hardware security, both finding vulnerabilities and building open source hardware, trying to make systems more secure. So he's going to tell you about that and asking hard questions.
Yeah, cool. Thanks for having me here. It's been a long time since I've been in this lecture hall. It's changed a lot. Like, they had hardwood chairs and the acoustics were terrible and you couldn't nap in them. But I think that was part of the strategy, was make the chairs uncomfortable so you could fall asleep. I'm going to talk about hardware security today with sort of an emphasis on supply chain attacks and verifiability. I encourage anyone, if you have questions or whatever it is, something's unclear, just stop me in the middle of it. I like to keep the presentation interactive. So today the topics we're going to cover are, we're going to talk about sort of, first, what are some of the ways of breaking hardware security. So we're going to talk about sort of direct attacks, if you have the hardware in your hands, what you can do with it, so direct physical tampering. And then what you can do if you can't actually get a hold of the hardware, indirect supply chain tampering attacks. And then we'll pivot from that into some potential mitigations, particularly around supply chain attacks, around what it means to make user verifiable hardware. A brief discussion about sort of plausible deniability and its role in the way it fits in the ecosystem. One thing that I wanted to mention for completeness, it's not in the deck, but just so you know it's out there, is that there's also a whole series of sort of tamper-evident and tamper-resistant techniques, anti-cloning techniques. So basically, hardening the walls of the hardware fortress, so to speak. But that it's a little out of scope of the presentation. So let's start with talking about breaking hardware security. So the thing that a lot of times people are trying to break into are things that are hardware security modules. It's security secrets that have been protected within a vault, so to speak, right? So up here on the left is a picture of like sort of a server grade HSM. They'll have a lot of features on the inside, like I mentioned, for like anti-tamper. If you take out the screws, they'll zeroize the keys on the inside. It'll have optical sensors. It has like motion sensors, all sort of stuff on the inside. It's debatable how effective any of them can be, against a determined adversary. It scales all the way down to smaller things like, when people buy a crypto wallet, that's a hardware security module. You're hoping to store some value on the inside. All the way down to the little SIM card that's inside of your phone that's meant to keep some private keys safe that allow you to authenticate yourself to the phone network. A lot of times, despite all of the sort of the external tamper techniques that are put around these devices, the security all kind of boils down to, at the end of the day, sort of the idea that you can put something inside of the chip and it's very hard to extract. Right? So you have some fuses on the inside, you have some secrets on the inside, and that, for better or for worse, is sort of what we've agreed upon is like a measurable minimum barrier that compromises a secure hardware device. So in terms of direct attacks that you can perform on hardware devices, here's an overview of some of the things that you can do. They're in two large categories, sort of passive attacks and active attacks. So passive attacks have little to no modification of the target system. So the idea is that maybe you can't run code on it, maybe you can't solder wires onto it, maybe you can, but you're not doing a lot of modification to the system, but you're sort of, and we'll go into that. And the active ones, there's basically no holds barred. You can basically do anything to the system, modify it, glitch it, do all these sorts of things. So from the passive side, so direct observation is sort of like the most passive thing you can do in many ways. If you can get say two samples of a target piece of hardware, they're identical, you can take one of them, completely decap it, etch away the plastic around the silicon, and look at the silicon on the microscope, and you see something like this. And you may be able to sort of actually read out so the implementation of the algorithm. You can even potentially see morphological changes in the fuses that store the secrets. And that would be with an optical microscope. Of course, today, the geometries are so fine, you have to have something like a scanning electron microscope. There's a picture of one that I actually happen to own. It's on a farm in Japan right now. I haven't been able to access it because of the pandemic and stuff. But they're actually surprisingly cheap to get in surplus. And you know, the idea with these types of things is that you would go ahead and you would open up a chip on the inside and you would try to look for it. This is actually a picture of an E-fuse element. And so an intact E-fuse looks like this, and then once they've actually gone and blown out a bit, you'll get a little gap on the inside, which you may be able to pick out with the microscope. A lot of times, of course, they know that people are going to do this, so they'll cover it up with pieces of metal, so you have to be a little more destructive to read the fuses out at the end of the day. But that would be sort of like the direct observation method. You can also not just look at it, you can measure the device as it's running. So this is actually an exploit that I pulled off while I was here at the Institute, where this is the classic Microsoft Xbox motherboard, and there was some secrets that went from actually this particular chip into the CPU over a high-speed bus right here. And I demonstrated that you could attach a device. This is actually hooked up to a board I was working on for my PhD thesis at the time. I happened to have it laying around with a lot of FPGAs. And so I just built a little interposer board that went onto the hypertransport bus and was able to directly measure the key material as it was going between the south bridge and the CPU. So that'd be an example of a direct measurement technique. And a lot of times people will put some price tag on direct measurement technique because they'll go to some Keysight thing and some really high-end test equipment, say they're like $250,000, knowing this is the barrier or whatever it is. This particular attack was done for like $150 over IAP. So it was like, if you can do a little bit of custom hardware, the cost can come down quite a bit. So another sort of passive attack is optical emissions attacks. Supposing you can actually see the chip, you've exposed to the silicon, or you can do backside imaging. There's a property of transistors such that when they flip, they will actually emit an infrared photon. And it's not, you can't see it in visual light. It's a very weak signal, but they will actually emit just a little bit of light. And so they have systems here where this is an optical image of the chip, and here is actually an image of it in infrared. And you can see here's a pair of clock drivers. They're really bright and sparkly. The RAM array is largely empty, but then you can see this pattern of bits here, which actually is representative of the state of some AES keys that's running on the device itself. So with these particular devices, you can actually see quite a bit what's going on. This technique was actually developed by chip designers to debug chips. So when you get a chip back and it's not working, how do you find out what's going on? They developed this sort of thing for failure analysis. It turns out you can actually just buy this machine from Hamamatsu for like $1 million or something like this. Put the chip in there, and you can actually get these readouts. So it's not an obtainium exotic technology. It's just expensive technology. Another form of passive attack is power side channels. So if you have a device that has a key on the inside, it's doing some computation. Every single time it does some computation, it'll absorb a little bit of power, right? If there's a difference in the amount of power that it takes to operate on a key bit between a 1 and a 0 state of the key bit, and you're doing sequentially, you'll see that as a pattern in the power trace. So you basically put a small resistor in between the power supply and the chip, and then you can get essentially a little bump that comes off here. You can see here, like, for example, this takes a little longer than that, which takes a little longer than that. And so effectively that can correlate to a property of a round of a cipher, a bit of the key. And so this is why a lot of people talk about doing constant time algorithms for cryptography and hardware, is because if you can actually get direct access chip and do sort of a side channel analysis on it, it becomes actually fairly trivial to read out a key with a technique like this. Another passive technique is RF side channels. So chips also emit in the radio frequency domain. This is what an RF probe looks like. They look like a little ring of wire that's kind of embedded in a piece of plastic, and this is actually another little ring of wire, these types of things. This is from a paper where they were able to put the RF probes over the AES engine inside of these chips, and as the AES engine was running, they would run like hundreds of thousands of traces decrypting the same thing over time. They could get enough averaging and denoising. They could essentially extract the key fairly reliably using an RF probe. Now, you'll note that the RF probe is really close to the chip, so this isn't like a thing you're doing from 10 meters away or something like this, but it still is a non-contact type of attack. You could imagine if you put a device on the table and the table has a probe embedded on the inside of it, you could maybe execute the attack on a victim piece of hardware. So those are some examples of passive attacks that you can launch on hardware. Now let's talk about some of the more active attacks. So sort of the ultimate active attack, if you were to ask me, that you could pull off is using what's called a focused ion beam machine, a FIB machine. And so it looks a lot like a scanning electron microscope. This is like sort of the size of a typical FIB workstation. And the idea is that you're actually launching ions, a beam of ions, gallium atoms in this case, and by adjusting the energy of it, you're either ablating away atoms on the chip, or if it's low enough, you can deposit atoms of that metal on the chip, right? So you can either cut or you can jumper with it. And at the end of the day, if you have a chip, in this case here, this is not someone hacking a chip, this is someone made a mistake, and they didn't want to spend $250,000 making another mask set, they're able to sort of drill down into metal layers, cut some wires, and then run some jumpers. You can see here they actually deposited a little bit of insulator here with some metal on top, so you have crossing wires. There's a whole, like all these things are basically is a cut and jumper fix to verify that a particular logic fix was working at the end of the day. So this is a very, very powerful attack that can be used to rewire chips at the chip level. So it would be sort of the ultimate thing to do. And a lot of people who have done work extracting, in practice, extracting keys out of, for example, satellite TV cars and stuff like that use this type of machine. So there's another form of active attack, a category I would call it fault injection. So there's several types of faults you can inject into a system. If I have a CPU and it's doing something interesting, I can use a laser to go ahead and stimulate it and induce a fault. So again, as like I said, the transistors, even though they can emit photons, by sort of the reciprocity signal, they'll respond to photons as well. An intense enough laser beam can go ahead and flip a bit or influence the computation. I can go ahead, and a lot of times CPUs that have a reset line on the inside, they'll have very strict length of time for the reset signal. Like you have to assert it for a full microsecond. What happens if it's less than that? Well, it turns out you get a partial reset or you get a glitch or something like this, right? So a lot of times people will go ahead and play around with this line here to scramble up the internal state of the CPU. Same thing with the clock line. You have the clock that's running, whatever it is, the CPU assumes the clock's going to keep running. You go ahead and stop the clock, or you make it actually run very fast for one cycle. You can induce a false state inside the CPU. Finally, you can go ahead and take the power from the chip, and you can, a lot of times the way the attack forms is you put a little shorting transistor on the power line. You can go ahead and glitch the power for just a brief moment, cause a VDD drop, and so if you're doing like a carry computation, a big long computation that would normally take a certain amount of time to propagate through, you drop the power, the carry doesn't propagate all the way, and then maybe you've changed a branch address or something like this at the end of the day. So the general idea is that you might have some flow that is, and you're going to compute some credentials, see if it's valid. If it is valid, do the secure thing, otherwise abort. So if you're going to, one form of a glitching attack is you want to actually run a total alternate code base. So in this case here, you're glitching, say, an address line for something that's being fetched. So you're going to say, instead of fetching the code from this block, I'm going to get from one page over by changing the high bit of the fetch. And instead of running this code, you run a completely different set of code which gets you to your final destination. Another form of it is that if you can time when the branch happens at the end of a secure computation, again, remember that trace where you saw, you could see like the shape of it, you can actually synchronize that and say, okay, at the very end of this is when we decide whether the key is valid or not. You can go ahead and glitch the clock, glitch the power, wherever it is, and instead of doing an abort, just go ahead and do the thing you want to do. Finally, another reason why you might want to glitch is that there's actually some ciphers where if you manage to scramble up the internal state, they'll leak private information. So RSA is infamous for having that property. So you don't even really have to be very precise about the glitching. You basically say, hey, I want you to sign this piece of material. You turn on the VDD. RSA kind of does something, I don't know what's doing, and the results come out actually leaking bits of the private key at the end of the day. So that's, there are some ciphers that have this property where you don't even really have to be very precise, but you can extract the data. It turns out that fault injection can be surprisingly easy to execute. So this is a real-world attack called the tweezer attack, spelled W-I-I, like the Nintendo Wii. This is the Nintendo Wii motherboard, and the attack here is this end of the tweezer is on a ground trace, And that one is on an address trace. And at boot time, basically, if you hold that tweezer in there, it'll hold one of the address lines low, and it'll cause it to execute from an alternate code bank that puts it into a different mode of operation. And it directly bypasses a lot of the initializations, and it was enabled these people to extract secret keys and whatnot from the inside of the device. So these types of glitching attacks don't need to be extremely sophisticated at the end of the day to be quite dangerous. Another form of active attacks is our coupling attacks. So this is a little bit on a different side. So if you have a piece of memory, there's an attack called row hammer. Some of you may have heard of it. And basically, the idea is that when you have a DRAM array, the memory is stored in an array, but actually this is a very abridged version of the size of the array. This is what it actually looks like on a scanning electron microscope. And these two wires would run like, it's probably the next building over to the building over there. They're very long parallel wires. And they make them as thin as possible because they want to make them very dense, which means they have a fairly high resistance at the end of the day. And the idea of the attack is you go ahead and you keep hammering those parallel wires on either side, up and down, until you've perturbed the state of the memory in the middle of it. And you go ahead and inject code in a particular area, modify a page table, some other secure value with a row hammer attack. So that's another example of an active attack that can happen on hardware. Another active attack that has become very popular recently is in discussions, particularly in academic circle, are the microarchitectural side channels. So in this case here, the idea is that you're running some code that can go ahead and leak information about the state of a computation due to timing differences in how fast the code runs. So, for example, this graph here, this graph here shows like if you have a Spectre path versus no Spectre path, the green versus the red line, you have quite a different shape in terms of the timing of the computation. Whether you can go ahead and flush the cache before or flush the cache after, or change a branch predictor or not change a branch predictor. And this whole class of attacks, there are mitigations and counter mitigations and whatnot, but it's complicated by the fact that CPUs have an immense amount of microarchitectural state on the inside that we don't know what's going on. And so people who are doing mitigations are essentially doing it empirically. They're like, I think this fixes this problem. We're going to run a lot of test vectors, but we actually have no model of the CPU on the inside at the end of the day. And then Intel goes like, oh, well, we're going to push a little firmware update patch or whatever it is, and then boom. Like everything's broken, or the new CPU comes out. So it's complicated by the fact that the good guys actually don't have all the information, and the bad guys have the advantage, and I just need to find one small hole that the good guys haven't patched, and they can leak private information out. So that's sort of like a summary of what you can do if you have direct access to hardware. If I can break into the data center, or if I have intimate connection to the silicon. But what happens if you can't access the hardware? More frequently, this is the case than not. Like, me walking into a Google data center seems pretty inconceivable. So the kind of another attack surface, a thing that I personally have been worrying about a lot, are attacks prior to installation. So this falls into the broad category of supply chain tampering. So the crux of why supply chain tampering is an issue is because the state of practice today for trusting a chip is literally reading the label on the box. What is inside this particular chip or not inside this particular chip? It's just like what's printed on the outside. Nothing more, nothing less, right? Which is not like a terribly good way to do it. Let me see. Actually, I brought some. Oh, yeah, I did. So I have, I don't know how much people get to play around with chips these days at MIT, or if it's all simulation or whatnot, but these are just some examples. I brought some just props along. People can look at what the idea is that as you look at these things, just ask yourself, how would you know if like inside these chips contain actually the thing you're talking about or not? I mean, it's fine if it doesn't make its way back to me. They're sort of just scrap samples. So I actually had encountered this problem personally. This is a board that I made, a little robot controller, has an FPGA on the inside. And I did a production run of them, and about 1.7%, something like 2% of them failed, right, on production. And I told the factory to hold them aside for me to analyze later. 2% is fine, right? Like, on a small production run basis, it's actually pretty good. I was like, okay, fine, I should probably recover these. I got the devices back, and then I was like, all of them were failing on this particular chip, saying it was bad. And I looked at the chip under a microscope, and I noticed that there's like a white square. And if you can look at it in the microscope image, it looks like it was ablated off with a laser, right? So the part number here is an XCS6LX9, right? Blah, 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 CSJ, whatever it is, all these, and so you think that would be, it looks like a legitimate Xilinx chip. It turns out that underneath this little square here were the letters ES for engineering sample. So what happened was that someone had actually gotten a bunch of engineering samples that were supposed to be disposed of, ground up, thrown away from the supply chain, lasered off the ES marks, and sold them as full genuine chips, which were failing tests because we had a test that looked at the JTAG ID of chips, and they have a different JTAG ID in the engineering samples than the real ones. And at the end of the day, like when the factory was receiving the chips, they accepted them because the guy who's in the material handling office is instructed to read every single character and make sure it matches what's on the bill of materials. Well, that white square is not part of their parameter of a thing to reject, right? Actually, a lot of chips have, like even this chip has like this white line. Is that authentic or not? Should that be there or not? Is the white square a problem or not? This is the state of the art that we have right now for accepting chips as real or not real. So as you just look at that thing, just ask yourself, like, how do we know what chip is on the inside? It turns out actually we don't really know what's inside of it. In fact, some of those chips you have there don't have good silicon in it for a reason we can go into later. So it's not just chips that get swapped out. Whole assemblies get swapped out without detection. So it's been disclosed, for example, the NSA has had a program to intercept Cisco routers and go ahead and carefully open up the anti-tamper seals, load them with alternate firmware, and seal them up again so they didn't look like they're modified. This is an actual document that was leaked in the Snowden leaks, where they show a USB cable on the inside that has an implant. On the outside, it looks like a regular USB cable, but on the inside, it has a device on the inside that can go ahead and record data and potentially for recovery later on. And then here is an example where people have found actual whole modules added to a motherboard. These are some JTAG implants that were found inside some Dell servers, right? And it's just another board they stuck on the board. But it looks, if you didn't know it's not supposed to be there, it looks pretty legit. You'd be like, okay, fine, like whatever, right? Another example that was recently found, this is actually the phone of one of the journalists that was involved in WikiLeaks. This is what the correct motherboard is supposed to look like, and this is what his motherboard looked like, and it has this box here that was installed on it, which contained a whole pair of FPGAs, a transmitter, a tap board for the microphone, a set of batteries, whatever it is. So basically, even though he had this full encrypted secure phone, someone within the vicinity could pick up a radio receiver and essentially intercept the call, despite the encryption on the device itself. He doesn't know when that particular implant arrived inside his phone. It could have arrived that way. It could have been implanted later on. But this is an actual sort of implant that was caught in the wild. So I think I like to sort of create ontologies of things to help me reason through what the things are. So we're going to go over sort of an ontology of supply chain attacks. I've divided along two axes. Difficulty of detection, so hard to easy, and difficulty of execution from hard to easy, right? And so, the general shape that I have are attacks like substituting a component, which is very easy to do and very quick, but also very easy to detect. Adding a component is pretty easy to detect, but can have a very difficulty of execution difficulty. We can go ahead and throw another chip inside of a chip package. We can go ahead and modify the chips. We can substitute chips. So let's calibrate what I mean by degrees of difficulty. So in terms of difficulty of detection, easy would be I can look at it. And if I knew what it was supposed to look like, I would see it. It's obvious. So those implants that we know about a lot of times because they're easy to detect, right? It's sort of like a survivorship bias in terms of implants. JTAG is also another easy way to detect them, that sort of thing. In the middle is I have to use an X-ray. So now I have to have some specialized equipment. I have to be actively looking for it, right? It's a little inconvenient. At the bottom, I have to get a scanning electron microscope. I'm digging into silicon. It's potentially a destructive operation to find the implant. In terms of execution difficulty, could be as less than $1 in seconds, depending upon like what it is. If I'm just swapping out a resistor, it's trivial, right? It's like a fraction of a penny and a guy in the right place. You know, in the mid zone here, I'm talking about tens of dollars in weeks to execute in terms of the development and the deployment of the incremental cost of the device. And then on the hard side, could be millions of dollars in months. Now, we're not talking about hundreds of millions of dollars, like millions of dollars in months. So it's like within the realm of like possibility, but not beyond like what, like for example, small nation states and criminal organizations can pull off. So let's start with substitute component. So this particular attack relies on the fact that a lot of components look exactly alike. These two resistors have different values. They look exactly the same. These two capacitors have different values. They look exactly the same. Why is this a concern? It turns out that a lot of systems will do things like set the order of boot in case something fails using an external resistor. So if I can't boot from the internal flash, I'm going to fall back to USB, and then I'm going to fall back to SPI, and then I'll fall back to JTAG. Right? That order of events actually has important security implications. You may want to make sure it falls back to an internal SD card before it goes to an external USB device. If you swap a couple resistors around, you can actually cause that order to change on a device, and it's very hard to detect because you would actually have to pull off the resistor or measure it directly to see if there's been attack. Another reason why this is important is a lot of times voltage regulators are set by resistor values on the device. So if you're going to try to season the device to make it easier to pull off like a glitching attack remotely, which is possible, adjusting those voltage regulator targets can give you an advantage. Same thing for the capacitors. If you're trying to do a glitching attack and you want to sort of season the device to do it, you can go ahead and derate the capacitor slightly. So that's why the substitute component is even on the board. But as you can see, it's very easy. This is not a high cost to deploy or execute. It's a substitute component. Adding a component looks like this, as I discussed. Because they're easily detectable, I think there's a higher awareness of this type of attack. Usually when they have the glossy pictures and stuff, this is the one that people think about in terms of supply chain attacks, right? But I think in practice, the bigger ones that are a little more worrisome are adding a chip inside of a package, right? So if you've ever used a micro SD card and you were to etch off the top with acid, you would see on the inside, there's a little piece of silicon that sits on top of the actual memory chip. This piece of silicon is the controller IC. They don't bake it into the flash memory because the flash memory process is optimized for doing flash. Controllers are optimized for doing controllers. And in fact, this was from a report I did where I had a bunch of fake SD cards, and I was trying to figure out why they weren't booting and why they weren't reporting anything, you know. Basically, it turns out people had substituted this chip out with a different type of chip. You know, they did that for cost reasons. They were trying to make a buck or something like this, but it's not hard to imagine. You can also have another chip that had a little bit of memory to go ahead and say, oh, if you're writing to a file with the name wallet.txt or something like this, make a copy over here, secret knock, the wallet comes out, right? And it turns out that, this is a very mature technology. Every micro SD card is built like this. And if you look inside like a micro SD card, like if you have those ridiculous 128 gigabyte cards and the thing the size of your thumbnail, right? It's actually multiple chips stacked on top of each other. It's like 16 chips stacked on top of each other, sort of wire bonded together intricately with these very thin wires and a controller chip. So this is like super mature technology. Like you can stack dozens of chips inside of a single package without too much effort these days. So is the solution against this to X-ray all the things? This is me trying to X-ray one of the circuit boards that I made to see what it would look like inside of a CT machine. Well, some things are pretty obvious in X-ray. So this here is an Ethernet mag jack, and of course, the first time some people see this, like, oh my God, there's components inside the mag jack. They're implants. These are completely normal. It's fine. They're toroidal transistors for the hybrid matching. They're not a concern, right? The less obvious thing is like, okay, we see here, this looks like a QFN outline. So this must be the silicon, right? Turns out, absolutely not. This is just the solder pad underneath the device. You can't actually see the silicon in any of these X-rays here because the first problem with X-rays is that silicon is quite transparent to X-rays. Right. So basically, when you look at this under an X-ray, mostly what you see are the copper traces, the solder, and the package itself. So here I've taken an X-ray and I tried to kind of tune it up as much as possible to sort of get that silicon. You can sort of see just the ghostly outline of the silicon right here. And this package here actually contains multiple ICs. This is actually a controller from one of those $9 phones. So it has 6 chips inside the package, and you can see all the bond wires going back and forth on the inside. And what's it supposed to be on even if I had the X-ray, I could see this. How would I know if the chip is supposed to be there or not? It's very hard for me to tell. So some mitigations for this, of course, if you use something like a CT scanner, we can get 3D information about what's going on inside the chip. Or you can maybe try doing some kind of spectroscopy or something like this, but it can be a little bit difficult to work through. Now, the second problem is that even if you could find a way to get the chips to resolve better, it's hard to trivially detect multiple chips inside a single package. So this here is an example of, this is actually one of the flash chips that would be used in an iPhone to store the whatever your 64 gigabytes of data inside your phone. It's a multi-chip stack, right? And so if you look at this in the X-ray from the top, we can see the bond wires. It's great, but how many chips are in this package? So if you actually cut the package on the side and polish it off, you can see all the chips on the inside and the bond wires going through. It's only until you X-ray it from the edge on that you get a hint that there's multiple chips on the inside. When you're X-raying the chip from the top down, it's very hard to see. So it's already hard to detect, pretty hard to detect these implants on the inside. So that's sort of this middle part here, add an IC in the package. We've gone through substitute, add a component, add in package. Let's talk a bit about sort of this harder area here, sort of IC modifications. What does that look like? So when you go ahead and you want to fabricate a chip, there's a few attack surfaces on the fab itself. This here is sort of like a toy diagram of what a chip design process looks like. You'll have some high-level design and some RTL, whatever it is, and then you have a big choice to make. Do you own the tooling to make the chip or not? If you don't want to make the multi-million-dollar investment to buy the Synopsys and Cadence tools and do the whole back-end flow, you're going to hand the RTL netlist to someone else and do what's called an ASIC flow to a trusted fab to compile and assemble that chip for you. You can see where this is going. If you have your own tooling, then you go ahead and you say, okay, we're going to go ahead and assemble our own chip. We have some blanks for hard IP. We trust the fab to assemble it. It goes through mask, processing, error correction, and finally mass production. So let's talk a little bit about the first attack surface here, and then we'll touch on these. So if you were to go ahead and do a ASIC flow, usually you'll do something like just an RTL, like register transfer hardware description, the code type description of the device, and then you hand it off to someone else. And you say, compile this and place and route it at the end of the day. This is actually a very popular flow for all the cheaper chips. So if you have the baseband management controller, the chip on the inside that controls whether the CPU turns on or not, but more importantly, has a management interface to the internet that allows you to remotely turn the chip on and off and write things over in the middle of the server's memory. That chip is typically done with the cheaper flows. So there's a trusted third party to do this. Disk controllers are done this way. Low to mid-end I/O controllers. A lot of chips are done using this particular flow. The COT, customer-owned tooling flow, is much more expensive. You have to spend several $1 million to buy the tool set, several headcount internally. It's necessary for things like flagship products like CPUs and GPUs and routers, but it's a much more rare flow. If you decide to go to the ASIC flow, you might engage with a company, for example, like SockIO Next to do it. They're a $1 billion company. There's a whole bunch of them. You've never heard of them. They're pretty small and anonymous, which itself is kind of an attack surface because it means they're not very accountable. And they'll offer here, okay, case one, give me a specification. We'll do everything else. Okay, they're completely implementing everything from the specification. Then when you give me the RTL, I'll implement everything else. Or you give me a netlist, and I'll go ahead and do the physical design. But you can imagine here, at this point in time, a lot of times actually, even when you say you've handed someone the specification, say, I want to have a USB controller, PCI, DDR4, whatever it is, they will add things to it like, we're going to add a debug interface for JTAG on the inside, and they'll do it in their way that will optimize their return on investment for doing your chip, which may include, exposing parts of your secrets, your buses, to an attacker at the end of the day. So that would be an indirect, not deliberate backdoor, but it oftentimes ends up being an exploitable backdoor in the process. Ranging all the way from this is sort of like the innocent backdoor to the full malicious, Someone has a national security letter. They know they're doing a particular chip, and they're given a little Verilog block. They have to go ahead and insert inside the chip, bury it on the inside. Don't tell them about it, and you're done, right? So that's the kind of the range of things that can happen on that flow. So, okay, ASIC flows are scary. So maybe we're safe just owning our own tooling, right? That's the solution if we want to do a trusted chip. Well, if you go ahead and own your own tooling, and you say you compile something down, this is an example of a plot. Each of these little squares here would be a standard cell, so like a flip-flop or a NAND gate, OR gate, AND gate, that sort of thing. But then say you want a block of RAM, SRAM. How do you make a block of SRAM? It actually turns out that you just leave a hole in your chip that is the size of a block of SRAM. You're not, as the customer, given the actual SRAM design, because the SRAM is fab proprietary. Foundries live or die by how many RAM chips they can cram onto a piece of silicon, especially today now RAM chips are mostly silicon. So they're not going to give you that piece of IP. At the end of the day, the foundry would go ahead and merge their proprietary block at the agreed upon connection points. So, you know, what kinds of things end up in hard IP? Well, stuff like your PLL, right, your ADC, DAC band gap, so that's pretty typical. Things like RAM, okay, that's a little more security sensitive. You can imagine now that fabs will do things like spare blocks of memory. So there's already more RAM in there than you expect to be inside your device. What is that RAM doing? How is it connected? ROMs, again, for density reasons, are not disclosed to users. eFuses, the things that you literally put your private keys into, are not available for inspection. I know people who work for very, very large phone companies who design their own security enclaves, and they have expressed frustration to me personally that we put all this effort in to build a secure chip, and we even managed to get them to give us the whole RTL and the PDK, whatever it is. The actual fuses themselves, they don't know what they look like. They're not allowed to inspect them. They're not allowed to know how it is. They just give them some vague properties of like, well, you have to blow 3 of them because we need redundancy because sometimes they fail, right? They'll have stuff like this because actually the fuses do fail. So if you design a fuse block, you have these weird rules like you have to put error correction on them and you have to blow them in triplicate or something because they're not reliable to blow. Why? I don't know. The foundry won't tell you, right? They just done a big characterization program. That's where your secrets go. Then things like pad rings, right? Okay, you don't get to see the pad ring that you're merging into. Okay, your I/O can now be tampered with, right? So at the end of the day, even if you do COT, there are still plenty of vectors for getting into the chip. Mask tampering is another sort of issue. So let's say you manage to get it down so you see the whole design and whatever it is, and you manage to convince the foundry to give you, you know, your eFuses and your SRAM. Great, I'm going to send my stuff off to TOPA and they have it printed onto a piece of quartz silica mask. Well, you're going to draw, you know, abstractly this blue shape here. It actually gets printed like this green shape here because they're doing, you hear numbers like, we're going to do 20 nanometer silicon, right? They're shooting it with light that's like 140 nanometers large. It's like sub wavelength. How do you do that? There's a lot of magic that happens. It turns out that if your design looks like this today, they're actually fracturing it into multiple masks and merging them together. This is a highly proprietary process. This is where like fabs live or die in terms of their margins and their yield and whatnot. There's a whole lot of IP there. You never get to see this sort of stuff. So your design already goes through a huge amount of processing. So even if you got your chip back, and you're kind of looking at it, you're going to see structures in there you didn't recognize. Like, why are there extra gates on this transistor? I didn't design these. And they'll be like, well, we had to add them there so as to protect your gate from over-etching or something like this, right? You'll get that explanation back, but you'll see mysterious stuff that you don't recognize. Also, masks themselves aren't perfect. Again, when you are making a chip and you're making that mask, if that mask has an error, then every chip has an error, right? Are masks born perfect? No, they're not. So there's a whole industry built around taking masks, finding problems in them, and then fixing them, right? Okay, so if we have, a short here, we can clean that up. If you have an open, we can bridge it. Okay, so now we're back into the situation of like, how do we know our masks haven't been tampered with at the end of the day? Well, what can you do with mask editing? There's some interesting papers, more on the academic side of like potentially tampering with the dopants on a particular transistor, changing the strength of the transistor subtly. This particular attack is very powerful because you can't even see it. Even if you delete their chip entirely and look at everything physically, you're talking about tampering with dopant atoms. So you have to figure out now how many dopant atoms are in a particular transistor or not. Maybe you can change the polarity of a gate, or in this case, they're biasing a random number generator by tampering with the doping. More practically, I think, the thing that you would do is a spare cell rewiring. Again, when you tape out a chip, you're spending millions of dollars on a mask set. The chip designer himself, the person or herself who's working on this thing, will be like, I don't want to blow $1 million and have it broken and not have a second chance to fix it, right? So what they're going to do is they're going to take a bunch of empty silicon and throw extra flip-flops and extra inverters and not connected to anything. They're just all around. And so if they have a problem, maybe with just one mask layer, they can go ahead and route an inverter in. So there's kind of a rule of thumb. Always have an inverter spare in hand to go ahead and like fix your problems. Guess what? It means that someone who also wants to modify the behavior of your chip now has all those things available. They only have to modify one mask set or omit a via or something like this to go ahead and change the function of the chip. So those would be sort of like the general broad brushstrokes of what you might worry about from the fab side. My personal fear, and I think this would be kind of the more practical, actionable attack, would be through silicon via plus wafer level chip scale package implants. So for people who haven't heard of them, wafer level chip scale packages are these. Basically, they look like pieces of silicon. They come as like raw chips, and they have solder balls directly attached to them. So this is an example of an actual package. It's delivered to me this way, and I'm supposed to put it on the board like this. The cool thing about this from the attacker standpoint is that you're given chips ready to hack, right? It's not like that chip you saw going around with the black epoxy on it. If I want to hack that chip, I have to etch away the epoxy, I have to pull off bond wires, I can damage the chip, whatever it is. These chips are given to me ready to hack. I don't have to do anything to go ahead and access the chip. The second bit of technology that makes this interesting is a thing called a through silicon via. So through silicon via is this is a piece of silicon, right? And there's some transistors here, and there's some transistors here, and there are two pieces of silicon bonded together. And as the name implies, we're going to dig a hole through a piece of silicon to the other side, and we can go ahead and put a piece of silicon in between two layers of active transistors. And this thickness here is on the order of a 0.1 to 0.2 millimeters, so like a hair thickness a bit. And this is now a mature. This used to be like science fiction, maybe about 6-7 years ago, but now it's in volume production. If you buy an HBM graphics card, wherever it is, they'll have through silicon vias already deployed. And so the way the attack works is if I take a look at a wafer level chip scale package cross section, this is the silicon I want to exploit. It has some solder balls. I would go ahead and build a through silicon via blank that's about the size of the chip. Most of the through silicon vias are just going straight through to the target silicon, and then the pads I want to do a man-in-the-middle attack on, do some substitution, tap, observe, whatever it is, are on this particular layer here, right? It's actually, so the threat side of it is that it's a very scalable in the sense that we target off-the-shelf chips. You don't have to bribe someone to give you raw chips, as in the case of a wire bond, because if you're trying to do a wire bonded chip, you actually have to pull off the bond wires, you risk damaging the chip. And so typically, oftentimes, you want to get the raw chips themselves, which means you're now bribing someone to get raw chips. In this case here, you're just buying them straight from the supply chain. There's no decap required of the chip. They're ready to hack. They're hard to detect, in part because it's such a thin layer of material that you don't really can't see it, and also because a lot of this is not ostensibly not a modified WLCSP, but it already has like a little seam on the side, and the reason is because they actually thinned down the silicon already during the production process, and they'll add another chunk of silicon to the back to make it easier to handle. It's just dummy silicon to make it easier to handle. So you already have a sandwich of silicon going on. Was this legitimate? Was this not legitimate? It's hard to say, right? This is going to have no X-ray footprint at all. And even though the through silicon via templates are going to be fairly expensive, probably in the order of hundreds of thousands of dollars to pull off, the template itself doesn't need to be in a high-end process, right? You can do it in a fairly old process, particularly if you're just trying to do an observation man-in-the-middle attack or something like this. You just need a little bit of logic there, and then the hard part is just getting the access to the etching process to put the through holes in. And to put that in perspective, the Pegasus malware that they've been using to target activists and whatnot, it's about $1 million a pop to go ahead and deploy one of those. So this is like in the range of the sort of things that you could imagine deploying. And once you've climbed the hill of buying these, building more of them is cheap. You're just buying, you're buying silicon and buying them onto existing chips. So it's a fairly scalable attack. So that's sort of like the ontology of supply chain attacks. Do you have any questions so far as to material I'm covering? Okay, good. So in terms of now in practice, what does the execution of supply chain attacks look like at the end of the day? So let's think about the attack surface of what it means to actually deploy these things. Start with you. You're the target, right? We're not going to talk about evil maids. They're a real threat, but that's not. If you're at the point where someone's willing to fly into your house, break into your house, and steal your equipment and do something with it, you're already in a very bad security situation. That's not you've kind of lost the battle already. So the more practical attack, it turns out, is that every single time something goes from a distributor to you, it goes through a courier. That guy is just following orders. Right? At the end of the day, who knows where the orders come from? And as I noted, there have been actual documented attacks on couriers where packages are rerouted, sent to stations for reloading and modification. Now, let's say you're not a state-level entity and you can't get access, you can't coerce FedEx to do something. What's another way you can do it? Well, it turns out that because we buy everything online, we can also return everything that we buy online to a particular distribution center. So if you want to, say, target a DC in a small town in Utah or something like this, and you know that the particular profile of people who buy things want hard drives of a particular type, you can just buy a bunch of hard drives in that area, return them to Amazon, and then you have a reasonable chance of them ending up in someone's computer after being modified. You have some statistical probability of that actually happening. And the cool thing is it didn't cost you anything for the material to pull it off because you got the refund on the material that you returned back. And so this is kind of like an everyday hack for everyday targets. It's particularly a threat against stored value wallets, so crypto wallets, because maybe if you're hacking hard drives, you're kind of phishing. Like most of the time, you're going to get not a viable target, not a valuable target. But if you manage to go ahead and hit on a cryptocurrency wallet, you know what's going in there is a piece of cryptocurrency, right? It's going to have some value. You almost always pull up a fish in that case. And so there's been some demonstrations of people, for example, demonstrating like, oh, this is what it looks like when we just, our first try to work through a tamper-evident label came out like this. It's not too bad, right? I mean, you might actually accept something with a problem like that. The basic idea is you buy the item online, hack it, return to the warehouse, profit, right? So it's actually, there are some cases of it documented happening, and it's surprisingly easy to pull off. Doesn't require diplomatic visas. You just get a tourist visa, go to the place you want to in the country that you want, buy things from the distributor, do your thing, return it, and you're done, right? Then, of course, once you've left the distributor area, a lot of times stuff have to cross borders through customs, where customs officers are literally deputized and allowed to open your boxes, right? That is within their reason to do it, and they don't have to say why. That just happens, right? And so if you go ahead and back it all the way out to look at the whole attack surface, it's pretty huge, right? All the way from, we talked about chip design, mass prep, chip fab. There's that element there. Then those chips go off to packaging, and those packaging guys are living on tiny, tiny margins. You have to remember, a lot of these people are not making a lot of money, which makes them very vulnerable to manipulation with money at the end of the day. Then, you have distributors, you have the people who are in the gray market, who are facilitate sales and trades, particularly in times like this when the supply is very lean. You have the product designers who will spec out components, boards, and assemblies, goes into a box build, finally a customs distributor, and then we have this whole other attack chain we're talking about. So there's a very, very, very large attack surface where you can inject potential implants inside of a device. So what can we do about it? Right, so this is a thing so this is where I kind of pivot from outlining the issues to sort of some of the things that's been on my mind lately, trying to figure out what we can do. So a popular question is, can open source save us? Right, so let's take this picture and have a GitHub repo on the outside, or a bunch of developers. This is all open source, right? Does this actually move the bar? The problem is with open source is that we can have an open design, open PDK, and open PCB, but then you have this whole attack surface before it gets to you. The place of check is too far from the place of use. So open source doesn't really help move that bar. And people say, well, what if we go ahead and require we have factories, like, in our particular region, like, let's do the European fab, like the trusted fab, whatever it is in a particular area. Marginal improvement because you still have couriers and whatnot in the way. So then what is the role of open source and trustable hardware? It still has a very important role, and I think it's primarily around design correctness. peer reviews, finding bugs, because we have bugs in hardware, and also things like Spectre hardening. So if we can go ahead and get all that microarchitectural state and model it correctly, maybe we can have provably correct mitigations for things like Spectre as opposed to this cat and mouse game of guessing what's going on. That's, I think, primarily the role of open source and trustable hardware. The big problem at the end of the day is you can't hash hardware. So I'm guessing you guys already covered things like digital signatures and hashing, so I don't need to review that. But with digital signatures, you can have a single bit change, and the hash is going to be very different. Very obviously have a problem. The problem with hardware is there's no convenient, easy-to-use method to confirm correctness immediately before you use it. So hardware is one big time of check versus time of use problem, talk to problem. I'll use this term a couple times over and over again through the lecture. It's all the way down to the bottom. So when do we check versus when do we use? So then people say, well, but Bunny, you once said there's always a bigger microscope. You're a hacker. You can pull secrets out of anything, right? And I'm like, well, that's true. We do have microscopes that, like, for example, tychographic X-ray imaging, where you can get these amazing 3D images of chips down to the gate level on the cutting-edge processes. Great for reverse engineering, great for design verification, right? First problem with it is that the light source for it is the size of a building. This is literally the light bulb for that microscope, is the size of a building. It's a huge light source in order to make that work. You're not going to be able to stick that in your backyard. And the other problem is it takes a really long time. I think I was reading a report that it's like 60 hours to image a 40-micron swath or something like that in that resolution in a very expensive light source, right? So you're not going to do this in every chip. You're really going to do this on a sample-by-sample basis. Which leads to the second problem is that when you verify one chip, you've only verified one chip, right? Would you accept that someone said, we're going to compute a digital signature on your browser once, and you're going to publish it somewhere, and that will be good enough. You can go ahead and download this browser and run it everywhere. No, that'd be ridiculous. You want to check the browser at the point of use. So just because you've checked just because 99.99% of the hardware is okay doesn't mean you're safe. A lot of times, unfortunately, a lot of security models are broken if even just one implant makes it inside of the server or the data center. So the question becomes, can we build an evidence-based case to trust our computers? What do we do about these types of supply chain problems? And this is the thing I've been thinking about a lot, and I boil it down to, I think there are 3 principles for doing this. First is that complexity is the enemy of verification, because we don't have hash functions. We're going to have to make compromises on complexity. We have to make things from the beginning designed to be verifiable. Second thing is we have to verify entire systems and not just components. There's some people who say, we'll just make one chip that's verifiable. That'll be fine, right? Turns out that's not good enough. And finally, we have to move that point of check to the time of check to time of use as small as possible by empowering end users to verify and seal their hardware. So the first one, complexity is complicated. So absent a robust, hashing function, verification falls back to literally sort of atom-by-atom verification, right? So if you want to tear apart your phone and look at everything on the inside, you've torn apart your phone, and now you might be able to get it back together again. And it's no longer useful at that particular thing. So more complexity makes it more difficult, and things are, there's more places to hide things, actually, if it's more complex. If we went more towards the simple side, say, okay, we're going to go ahead and build microprocessors out of discrete transistors, like this thing called the Monster 6502, that someone did, that you can literally build a device out of discrete transistors. That's great. That's very verifiable. But the problem is, at the end of the day, is that it runs at 50 kilohertz and it's 8 bits. You're not going to do curve 25519 on that any sort of reasonable amount of time. So there's a trade-off that faces system designers. If you want security, you're going to have to think about what features do you really want. And the way I like to pose is that these 2 devices ostensibly do the same thing, right? They're both headsets with microphones on them. The difference is that this one here has 1 transistor. It's the little FET that's inside the electric the microphone that is used to amplify the input, and everything else is just Maxwell's equations. Like, you can take it apart, look at the coils, see what's going on, a piece of copper going on. Very simple to verify, does what you want it to do, right? This, on the other hand, is magical, right? Fits in your ears, runs on power, whatever it is. It's got, probably like close to 100 million transistors on the inside. How are you going to verify it, right? The 2 basically do the same thing, but the verification challenge is orders of magnitude different between the 2. So you have to make some compromises. We don't get the magical devices with wireless connections if you want something that is verifiable. Now I say you have to verify entire systems and not just components. And so this goes back to the idea that, there's a lot of like phone companies that will advertise, oh, we have a secure chip that we keep your private keys on the inside of, right? Trust us, we have Knox and we have like the secure enclave and all these sorts of things. There's a problem that I call the IME problem, the input method editor problem, is that yes, you can go ahead and keep a piece of secret on the inside, but then at the end of the day, you're typing stuff in plain text and you're viewing stuff in plain text on the device, and that's all going through keyboard and a display, right? And at the end of the day, what matters to you is not this secret, it's this secret at the end of the day. That's what matters to end user. And the number of times, I don't know if people here use Android phones or whatnot, but have you ever seen this particular prompt when you install an editor and it says, oh, this thing might be able to collect all text you type, including personal data like passwords and credit cards and whatnot. And then you just go, okay, right? This is like, at the end of the day, you don't need to have a backdoor in Signal or your secure messaging app with end-to-end encryption. We can go ahead and say, all right, we're just going to go ahead and, talk to the people who do your real virtual keyboard program and mandate data collection there and upload the data with timestamps to the cloud. You can go ahead and piece together the collections of just timing attacks at that point in time with the input method editors on either side. So this is a very effective attack, particularly if you can control the app ecosystem and what gets deployed. So that's why it's important you have to verify the whole thing. What we care about at the end of the day is the user's secrets. Private keys are not the same thing as your secrets. Finally, we need to empower end users to verify and seal the hardware. So when I say empowerment, I mean at multiple levels, not just at one particular level. We have all the way down to the, ideally to the silicon level, to the board level, to the design level, right? So you want to have all these documentation disclosed. How do you even know what the thing's supposed to look like? Those Dell servers with the JTAG implants on the inside? Like, maybe an expert can look at it and be like, why is there something plugged in the JTAG port? But the typical SRV, you look at me like, oh, it says Dell on it. Great. We'll go ahead and like plug it into the server rack and go for it, right? So you have to have something published, a reference that people know what's going on. So, trying to turn this into something more actionable, I've actually built a little device here. I'll let you sort of pass around if people want to look at it. This is an actual sample of what we're building. I call it Precursor because it's not complete yet. It doesn't quite do a whole lot, but we're getting to the point of being able to do something. And the idea is we want to facilitate evidence-based trust. It is a device. It looks a bit like a phone. It's simple construction. It's open design. And it's sufficient in function. And really one of the questions I'm trying to look at is that human-computer interface issue, right? Getting HCI is a huge issue in security because basically humans are becoming the weak link right now. It's not so, our ciphers, we have ways to prove them. People do formal verification. We can find all kinds of, close down all the, the channels, whatever it is, and then you go ahead and just call someone up and say, hi, I'm from your ISP. I need to get your password so we can unlock something. And someone goes, okay, sure. I'll go ahead and give you my password, right? That's more and more basically the final frontier in security. So on the one hand, we have devices like this which can provide security. They're simple. They're very probably easy to verify if we can actually get the plans for it and know that it was true. But it's kind of a little bit too simple. People don't like these. They're hard to use. You don't know what you're typing into. You have to punch a bunch of stuff in. This, on the other hand, we have browsers. Everyone wants to have a browser. It wants everything, I want to have my password manager inside my browser because that's where I type it in, whatever it is. The problem is that even though they're very featureful, there's like intractable attack surface. Like we're literally inside browsers inviting people to execute code on our device. We talk about remote code execution exploits. We literally take remote code and we run them without knowing what's on it in the form of JavaScript in every single web page that we have, right? So we already have invited a lot of trouble because we have this very featureful thing. And so what I'm trying to find here is just enough and no more. What's the right amount of material to cover up the attack surface and no more than that? So what functions can this device do? It's designed mostly for single application deployments of things like secure messaging, voice chat. It has multilingual capability, can do password management or crypto wallet. It's not designed for web browsing. It's not designed for games. It's not designed for photos and videos. So you notice it's like a black and white screen with a plain old text keyboard. Very simple device, 100 megahertz RV32 iMac. with an MMU and AES instructions. It's running on an FPGA, has a Curve 2551 accelerator and SHA-2 accelerator in it. 16 megabytes of RAM, has a little LCD on the inside you can see. Audio input is only via the jack, so there's no microphone in it. So when you pull it out, there's just no microphone. And we run a full custom OS called Zeus on the inside. It's a QNX-like microkernel. We wrote it from the ground up, written in Rust. So the device itself is simple in construction. So this is what the device looks like when it's torn apart. It's, unlike, modern smartphones, which have like the bonded-on touch screen and all this sort of stuff. It's designed to be taken apart, 6 screws in the front bezel, a tub case CNC in the back, circuit board you can look at, all the other parts you can inspect. Like I said, it has screws in the front to help you inspect it. So the reason why we went with the physical keyboard is that wires are visually inspectable, right? It's a 2-layer daughter card. It's actually made of a special transparent material. You can just hold it up to the light and be like, okay, look, I don't see anything on here. Trivial. That's like trivial inspection. Sufficient in function. It's a keyboard. And the way we do multilingual on this is we actually have these little plastic overlays. And I have overlays in Azurity, QWERTY, Dvorak. You'll see that one's in Dvorak. We have a complete black one, so if you want to make your own, we have a Hangul overlay. So people can go ahead and make their own overlays. So that's how we solve the multilingual problem in the physical domain. Whereas if we wanted to do a touch keyboard verification, it can be very hard. If this is a typical sort of touchscreen controller, it has a firmware rev on it, right? You think you're buying a chip, right? But the thing is running a piece of firmware, and it can be updatable, right? And I don't get to see it. So if I went ahead and built this whole system, and I went ahead and decided to throw one of these on the inside, I feel like I'm back to where I started. The LCD itself, like I said, I want the screen to be verifiable, right? So there's a high DPI, 200 DPI, black and white screen, 336 by 536 pixels. All the drive electronics for the LCD are built on the glass itself. So this is actually, with a 50x zoom optical microscope, we can actually see, these are the address decoders for the individual pixels here on the screen, right? So you can literally verify it with a simple optical microscope, as opposed to a color LCD, which if you ever take one apart, this is a small one, but the big ones have the same thing. You'll see a very long rectangle, slim rectangle like this. That's a piece of silicon. It doesn't look like it because they potted it in some epoxy to keep it from falling off. But if you look at the other side, on the back side, you can see how complex it is. This is actually done in a fairly advanced process. It has a full frame buffer on the inside, has a command interface. Again, we're now into the situation of putting something fairly complicated that we can't inspect in the inside of the device. So this is an example of what the board itself looks like. We are sharing documentation so that people can be educated and know what to look for inside the device. And so that's part of the experiment of this, is to see, will the users actually use this to verify the device? What are we missing? What do people want to do? And the board itself is actually designed along attack surfaces so that you don't have to spend so much time verifying things. We can call out, okay, this is where the TRNG is. Here's the keyboard. Here's the audio. Here's the bus. All these types of things. You can look at the particular things you want to look at and verify them quickly. Which leads us to the hardest problem, which is verifying the CPU itself. So now we've gotten the I/O, and we've gotten like the board level and stuff like this. So as I said, like silicon inspection is typically destructive and hard. It's difficult to check and use a specific chip. So this is a great picture of a chip that IBM put out, but you noted they cut it, right? I mean, this chip is not going to work anymore. You can see what's on the inside, but you're not going to be able to use it, right? So what are our options for non-destructive silicon verification? If I was to have my way, and this is sort of like a later research project, kind of years to develop kind of thing, I would use something like optical fault induction to do it. So silicon is transparent to lasers at 1300 nanometers. If you had a flip chip, I think one of the chips going around you saw had a silvery piece. That's actually the back side of the silicon completely exposed. So if I were to hit that with a laser at 1330 nanometer, it goes straight to the silicon, and I can stimulate the transistors, or more importantly, I can see the reflectance of them. I can see it modulated off the transistors, right? Now, you'll note that I said that the laser is about 1300 nanometers. What is the geometry of a transistor? Much smaller than 1300 nanometer, right? So really what you're going to see is not individual transistors. What you're going to see are standard cells, or more importantly, interference patterns of standard cells. So we won't be able to reason about this down to the wire level, but this is a hell of a lot better than just looking at a package and be like, looks right from what it says on the outside, right? So now we're down, we've at least constrained the attack surface to fab level stuff. And this combined with some BIS techniques, built-in self-test techniques, so some JTAG scans and whatnot, and some other techniques we're thinking about, I think we can get it to the point where we can get a fairly high assurance that we have a verified piece of silicon. Years to develop, like I said, this is a thing that in my wildest dreams I'll be able to get the funding and the manpower to do it, but that's what we're thinking about. The solution today is to use a field programmable gate array. How many people know what an FPGA is here? Yes. All right. They teach this now. But, anyways. I actually gave us a similar lecture recently in Amsterdam, and no one knew what an FPGA was. So I don't have to go over it. So FPGAs are like big arrays of logic and wires. They're user-configured to implement hardware designs. And the idea is that you can go ahead and narrow that talk-to gap, that time of check to time of use gap, by compiling your own chip, right? So we ship you the source code. You can look at the source code. You can do a digital signature on it if you don't have the time to verify the source code itself. And you can compile it down on your local machine and transfer trust in like software. The bitstream itself is also can be signed and whatnot. So the subtlety with this, of course, is that the tool chains themselves may not be open, and there's questions about whether there are implants in the tool chains. But there are people who are working on solving this with some free open source flows that can target our particular chip. So the idea is that we can go ahead and essentially turn the CPU into a software problem. And part of the reason why that works is that FPGAs themselves are a little bit like ASLR for hardware, the compilation process. So the address space layout randomization technique, which you may have encountered, I know, earlier in the course, where you go ahead and when you're at link time, you go ahead and shuffle things around to try and make it hard to do a heap spray exploit or whatever it is. This is 2 runs of a compilation of the same code. And, the same particular cell here was, this particular net is mapped to a very different place on one versus another, probably about 10 items off in terms of row column offset, right? And that's with just the way we do it, we just change a random seed in the compilation to go ahead and force the layout to run differently. So what does this mean from a practical standpoint? If you wanted to go ahead and flip the high bit on the program counter, you would need to know where that particular cell is. So if it's located here on one chip, it's located there on another chip. Well, if you want to have a high assurance of getting it, you're now putting all of a sudden a fairly expensive employ in every single one of these little tiny logic cells. The size of your chip will be multiples larger than what it is, and you don't even need an X-ray to see that. You'll just see that the chip is just too big at that point in time. Consume too much power, too much leakage, blah, blah, blah. So it sort of tilts it back towards the realm of having some modicum of confidence. Just for, I don't know, shits and giggles, this is what it looks like on the inside of the actual chip itself. This is what we're deploying today. So we have, it's all open source. It's a fairly complicated chip with a bunch of accelerators on the inside if you want to dig into it. I actually have a video recorded from boot to root in 1 hour. It's at this URL. And so the idea was I wanted to, just as a reality check on myself, have we made it too complicated that I can't explain it to you? So if you really just want to do a deep dive specifically into this project, in 1 hour I go from the entire thing of compiling your own SoC, looking at the reset vector, tracing it through, going through root key provisioning, going through the actual boot process, the OS, everything in 1 hour. So that's in one video if you want to really do a deep dive into that. So that was sort of a test to see if we've gotten too complicated. I think the answers were just at the hairy edge of what we can do in terms of complexity for verification. So that's that particular device. I would like to get that thing back eventually. The chips themselves are more fungible, but those are a little rare. So now I want to talk a little bit about, switch gears a bit and think about sort of the meta question about what about direct attacks against users? So we're putting all this effort in to build strong security. So we can't crack the crypto, and we've got formally verified algorithms, and we've got side channel resistance, and whatever it is. At the end of the day, this now just pushes the problem to us, right? We become the weakest link. So lawful and unlawful coercion of secrets through search, seizure, and subpoena become the primary attack vector, right? And there's this philosophical debate, should security prioritize the user safety or the secret safety, right? And so this is like a classic XKCD, where like, in the crypto nerd's imagination, we're going to build this, we want to get some data out, and like, oh no, it's like encrypted with 49.6-bit RSA. Okay, here's a $5 wrench, beat it out of the guy, and get them to, there's a lot of reasons why this is not exactly the way the Sierra works, but it makes the point that humans become the weak link. Now the thing is we have to remember that in practice, security is a function of social context. Do people still pick locks here at MIT? Is that allowed, or they shut that down? Yeah. Did anyone do it's dead now? The sort of pick lock. Oh, okay. It's on record. All right, whatever it is. Anyways, back in my day, we could talk about it. You would be like, oh yeah, I'm in the hacking club. We pick locks. We were like, we're in 10250 the other day, walking around after dark, right? That was the thing that was okay. But the thing is that locks can be picked, right? And doors remain locked not because locks are effective, but because there's a social context. We don't pick the locks because there are consequences to picking locks. They don't stay closed because the locks are strong. The alternative way to look at it is that police rarely have to pick locks. If a police wants to get into a door, they don't say, oh, I got to get the lock pick. Oh, damn, I can't pick the lock. They just get the key. They just come up with a warrant and get you to open the door, right? At the end of the day, there's a social context to security, right? And if there's one thing I've learned watching news since 2016 is that if you're under investigation, plausible deniability is an extremely powerful tool. The number of people I've seen get away with ridiculous things by saying, I do not recall, I don't remember, I don't know what this is, I've never heard of a burner phone, I've never, I don't recall this and that, is like ridiculous, right? So some lawyers will say that you should never try to lie under oath, of course, right? But there's a thing about plausible deniability where maybe you can get yourself at least more time, and time is critical in some situations. You can get yourself out of a particular detainment at that point in time through a board or whatever it is. Plausible deniability is a very powerful tool, and I would like that to be a property that a security system gives you. Because part of the problem right now, actually, a lot of security systems is they're very secure, but they're also very provable what's in security on the inside. I can say, you have exactly these secrets, and these are the passwords, and I have a warrant for these 10 passwords, and you cannot get out of jail until you give me all these 10 passwords, right? So, effective plausible deniability the requirement is that an omniscient adversary cannot prove or disprove that a secret exists on the device. So I've taken your device, I've done a full forensic analysis. I can't be like, here's the password file. There are 3 users on here. I want the passwords for each of these 3 users or 3's account. That can't be there. So there's a few techniques to counter that. So for example, you want encrypted data to be indifferentiable from free space. That's a free space wipe. That's a well-known technique. You want no metadata leakage. So basically, you don't want to have there's like a big, there's a file called secrets.txt.gpg. That would be like a pretty obvious tell. I want to go ahead and decrypt that particular thing. So they have some encrypted file systems that offer this. So you can detach headers on a Vericrypt volume or whatever it is, and so you can't tell what part of that white noise is data or if it's just free space. But more importantly, one thing that hasn't been addressed, at least in the literature that I've seen, is that the applications will tend to leak pointers to encrypted data. So even if you did this particular technique where you have another volume where the secret's on, the application itself oftentimes says, oh, the last time you opened a document was on f:secrets.txt, right? And then you've unmounted that particular drive, and then the inspector opens it up, goes to your recent secrets, tries to hit it, and says, oh, it's not there. And then, okay, how do you deny that existed at the end of the day? So this is called the API, the application level leak of pointers to encrypted data. So no password-specific salts and usernames, no dangling file references, no records of the browser history. There's another paper that Bruce and I wrote about this. You can read about sort of the state of the art there. My solution to this, and we're deploying it in this particular platform, is the plausibly deniable database. So it's a key value sort where the KV pairs are stored in the dictionary. And the dictionaries themselves are then stored in what I call a basis. So a bunch of dictionaries together form a basis. And the user view is a union of one or more bases. So here is the user view, and there's a line here between the internal view. This is what the PDB sees on the inside. I have basis A and I have basis B. And I have maybe, say, a dictionary for contacts and some passwords, and this is in basis A. And basis B, say, I want to keep secret at the end of the day. There's a contact here. I don't want anyone to know about Trent, who's living at 58 Manchester Road. And then the user view on this side is automatically unionized into a single dictionary and a single dictionary for contacts and a single dictionary for passwords, right? So the application itself doesn't need to know that these two bases exist. The application just give me the thing for contacts and the thing for passwords. So this mitigates API deniability leakage because when you go ahead and lock this particular basis out, that information is taken out of the union view. These dictionaries still exist, but that data is gone. So now the application, at the application level, you don't have to be aware of the plausible deniability issue. You just basically make sure you're not doing stuff like caching state inside the application itself. You always go to the disk to fetch your contact list. You'll be fine, right? Just don't store a copy of it internally. And so in order to mitigate forensic disclosure, basically the trick is that as long as a lock basis is indistinguishable from free space, looks like noise, then a forensic dump can't particularly say, if I have lots of free space or if I have lots of secrets. And there's a formal definition of what the property of the cipher needs to be to achieve that. And so we use AES GCM SIV to go ahead and achieve that on a page-by-page basis. Now, the idea is that each of these, we take the two bases and we split them up into pages that are stored in disk, and they're encrypted to different keys. And if the key is not there, you can't access the data. Now, scanning through the entire disk to look for the data is going to be pretty slow and unusable. So the details around this, and I'll just kind of blow through this quickly and make it run fast, is that each of the bases has a structured map into a virtual memory space. They all have an independent 64-bit address space that is identical for each of the bases. So my root block is in address 1, and then the dictionary list is in this area, the key list is in this area, whatever. It's identical across every single basis. This goes through some randomized permutation map into a page table. Each page table entry is encrypted with AES ECB, a very simple, not terribly good cipher, but a very fast cipher to decrypt. And the page table entry itself has the virtual page number that corresponds to, some flags, a nonce and a checksum. And this nonce and checksum aren't meant to be strong, it's just meant to be fast, to say, do I have a candidate page or not? So you go ahead and blow through this and you cache which ones look like they could be good pages. And then later on, when you want to access it, there's a linear map to the actual data itself, and you can do the expensive operation of doing the full authenticated encryption to verify the data itself. When the data is not there, it looks like noise. When the data is there, you can go ahead and sum it up. One problem with this is that free space is lock bases are indistinguishable from free space. So how do I allocate a block without erasing some data is the question. So so the solution to this is that when you first create or when you want to allocate some free space, you ask the user to map all the known bases. They have to do this in a secure location, so sometime prior to, say, a customs inspection or whatever it is. You go ahead and pick out a random subset of free space equal to about 10% or so of the disk and call it definitely free space. Relock all the secret bases. You allocate from the free space until it's exhausted. And then when you're out of memory, you go back to the first step and you repeat, rinse-lather, repeat. So the general properties of the PDDB is that when you erase the basis, it's equivalent to forgetting the key. So if you say, I do not recall, it is the equivalent of saying the data never existed or it is erased. Right? So you can say that with like straight face and know that as long as you can repeat that over and over again, you can't be caught. Against a single forensic imaging event, so some attacker says, "I don't believe you. I'm going to image the whole device out." The attacker cannot prove or deny that all basis passwords have been disclosed, but they can force the deletion of undisclosed secret bases by just forcing it to download a huge file and just repeating that free space allocation algorithm over and over again. But in many cases, that's actually a desirable outcome. You may want to just erase that file, and you basically destroyed the evidence in the process of the inspection. You get diminishing deniability versus repeated forensic imaging events. So if you're crossing a border multiple times a day and someone's imaging your disk and they can go ahead and see what the ciphertext looks like and get a map of it, you have some diminished deniability. But you can go ahead and re-encrypt and reshuffle the disk as well. But it's a very expensive operation. One problem with this is that when you first create or when you want to allocate some free space, you ask the user to map all the known bases. They have to do this in a secure location. So sometimes prior to, say, a customs inspection or whatever it is, you ask the user to map all the known bases. And then you go ahead and relock all the secret bases until it's exhausted. And then when you're out of memory, you go back to the first step and you repeat, rinse-lather, repeat. So the general properties of the PDDB is that when you erase the basis, it's equivalent to forgetting the key. So if you say, I do not recall, it is the equivalent of saying the data never existed or it is erased. Right? So you can say that with like straight face and know that as long as you can repeat that over and over again, you can't be caught. Against a single forensic imaging event, so some attacker says, I don't believe you. I'm going to image the whole device out. The attacker cannot prove or deny that all basis passwords have been disclosed, but they can Finally, just to say, the PDDB is not a panacea, right? Deniability is fundamentally a social tool, but security always exists in a social context. And also, not everyone can execute deniability to the same proficiency. It takes some training, some coaching on how to think through it and be able to deny, but it's a thing that people can be trained to do. Deniability is optional, and it's not always appropriate for all situations. Again, it's a social context thing. However, the thing is, at the end of the day, nobody can deny anything without the option of strong plausible deniability. So the reason why I wanted to put this in here is to give people the option. So they should choose. They have the tool in their pocket to exercise this and gain that tool that I've seen used over and over again in the past few years, plausible deniability, to get out of investigations. So it's just one of many tools that are needed to help navigate the upcoming legal challenges to privacy and security. And so with that, I think I'm almost out of time. I'm going to open up to Q&A. Just a reminder, this is that video if you want to look more at Precursor about the boot to root. You can reach me at, I don't know, various socials, whatever it is, and obligatory thanks to my funding agency, NLNet, who has been giving me grants to make this research possible. So thanks. So we'll take some questions if we have any time, but I think I managed to almost use all of it up. Yep.
What's the battery life on Precursor?
Battery life on Precursor is a very good question. If it's full bore running with the FPGA on, it'll last about 12 hours or so. But if it's on that standby screen, it can last for about 3 or 4 days. So it was actually very tricky to get an FPGA to have a good battery life. But, yeah, it's not easy. It's one of the system challenges. Yep. How do I verify that FPGA chip is actually secure? I don't and I can't, but the idea is that we're relying upon either the recompilation to shuffle the blocks around, so that if there is someone trying to do an attack on the device, they would have to exploit every single piece of the chip. And also there's some tools to go to do bitstream analysis to make sure the bit streams are valid. Yeah. That's right. Yeah, the chip itself could have some hardware probes or stuff on the inside, but part of the idea is that you can do things like we can go ahead and thank you. We can shuffle the pins on the outside. We can permute like the RAM access pins. So if there's someone doing an I/O level exploit on it, you can go ahead and do that. And then we've tried to enumerate the known backdoors at least. There's like an inspection backdoor and things. We lock them down. But for sure, yeah, it is an open question how much you can know about it. But the idea is that even if the chip, first of all, if someone were to try to pull off a meaningful exploit on it, they would have to make the chip much larger in the area because they would have to implant every single gate, or you can just basically recompile the chip or do any number of mitigations to try and get around it. But it's not perfect at the end of the day. Yeah. There's a question over there? The hardware accelerators for crypto are inside the FPGA as well. Yeah, the Curve 25519, the SHA-512, the AES are all in the same. If you